opaque identifier from the perspective of HTTP. What is being done is not really versioning at all, it is simply creating a brand new media type. As far as HTTP is concerned, media type identifiers are opaque strings, so no meaning should be inferred from the characters in the string. So, in effect, application/vnd.acme.foo is no more related to application/vnd.acme.foo.v2 as it is to text/plain. The identifiers are different, therefore, the media types are different. The fact that the parsing library for the two versions might be 99% similar is an implementation detail. A downside to using media types to version is that it exacerbates one of the existing problems with server-driven negotiation. It is not unlikely that a service may use many different media types to expose a wide variety of content, requiring that a client declare, on every request, all of the media types that it is capable of rendering adds a significant amount of overhead to each request. Adding versions into the mix compounds that problem. If a client supports V1, V2, and V3 of a particular media type, should all of them be included in an accept header in case the server is only capable of rendering an old version? Some user agents have started to take the approach where they only send a subset of media types in the accept header, depending on the link relation being AC. CEST. This does help reduce the size of the accept header, but it introduces an additional complexity where the user agent must be able to correlate link relations to appropriate media types. Versioning in the URL. Versioning in the URL is probably the most commonly seen approach in public APIs. To be more precise, it is very common to put a version number in the first segment of a URL, for example, http://example.org/v2/customers/34. It is also the approach most heavily criticized by REST practitioners. The objection is usually related to the fact that by adding URLs with a new version number, you are implicitly creating a duplicate set of resources with the new version number, while many of those resources may not have changed at all. If URLs have previously been shared, then those URLs will point to the old version of the resource rather than the new version. The challenge is that sometimes this is the desired behavior and other times it is not. If a client is capable of consuming the new version, it would prefer the new one instead of the old version that it bookmarked. If the resource with the new version is actually identical to old version, then it introduces a new problem where there are two distinct URLs for the same resource. This has numerous downsides when you are trying to take advantage of HTTP caching. Caches end up storing multiple copies of the same resource, and cache invalidation becomes ineffective. An alternative approach to URL versioning is appending the version number near the end of the URL, for example, http://example.org/customer/v2/34. This allows individual resources to be versioned independently within an API and eliminates the problem of creating duplicate URLs for identical resources. Clients that construct URLs have a much more difficult time consuming this type of versioned URL, because it is not as simple as just changing the first path segment in all request URLs. Hypermedia-driven clients can't even take advantage of this type of versioning because URIs are opaque to them. New resource versions must be identified via a versioned link relation to be accessible to this type of client. Versioning of APIs is a difficult topic that has many pitfalls. Making the effort to avoid versioning as much as possible will likely provide many long-term benefits. Walking the walk so far in this chapter, we have discussed in general the pros and cons to developing evolvable applications. At many points in the development of an evolvable distributed application, you'll have choices to make, and the right answer is frequently it depends. There is no way, in any reasonable number of pages, to consider every possibility and every outcome. However, there is value in demonstrating a particular set of choices to a particular set of circumstances. In the remainder of the chapter, we will focus on a specific application that presents common challenges, and we will consider the options and make a decision. In no way are we suggesting the choices we will make in the following chapters are the best for every scenario, but they should be illustrative of the types of decisions and choices that you will need to make while building an evolvable API. Application objectives. It is always challenging to pick a domain for a sample application for demonstration purposes. It should be realistic but not to the point of getting bogged down in domain details. It should be complex enough to provide a wide range of scenarios but not so large that the architectural guidance gets lost in the implementation details. To eliminate the need for you to learn domain specifics, we chose a domain that software developers are already familiar with: issue tracking. It is an area in which we have all seen a variety of implementations of both client and server. It is naturally distributed because its primary focus is communicating and sharing information among different team members. There are many use cases that surround the life cycle of an issue. There are many different types of issues that have their own set of distinct states. Issues have a wide variety of metadata associated with them. Goals: we want to define the types of information that we believe fall within the domain of issue tracking. We wish to define the minimal set of information required to represent an issue. Define a core set of information that is commonly associated with issues. Identify relationships between the information in our system. Examine the life cycle of an issue. Identify the behavior associated with an issue. Classify the types of aggregations, filtering, and statistics that are done on issues. This is not an attempt to exhaustively define the ultimate, all-encompassing issue SCHE. Our objective is not to define functionality for every possible scenario in the domain of issue tracking, but to identify a common set of information and terminology that delivers value to people who wish to build some form of issue tracking application, without limiting the scope of those applications. What we are defining will evolve. When you look at different applications that attempt to address the same domain, you will often find they have taken slightly different approaches to the same problem. We are looking to identify those differences where it doesn't matter which option is chosen. Let's just pick one, or enable both. When we eventually distill this domain down into media type specifications, link relations, and semantic profiles, we should be left with a common ground that enables a degree of interoperability without limiting individual applications from providing unique features. Opportunity: the domain of issue tracking is ripe for improvement. There are dozens of commercial and open source applications that address this domain, and yet they all use proprietary formats for interacting between server and client components. Issue data is locked in proprietary data stores that are tied to the application that created that data. We are limited to using client tools that were designed specifically for a particular issue data store. Why can't I use my favorite issue management client to manage both the work items defined in my bucket repositories and in my Git hub repositories? Why do I even need multiple stores? No one ever considered writing a web browser that is specific to Apache or iOS, so why do we insist on coupling client and server applications in other domains that are focused on distributed data? Unfortunately, the type of sharing and reuse that the web architecture enables through the reuse of standard media types does not appear to be in the best interests of commercial organizations. Usually, it requires open source efforts to get the initial moment going before commercial organizations take notice and realize that integration and interoperability can actually be major benefits to commercial software. Information model. Before we can begin to develop web artifacts like media types, link relations, or semantic profiles, we must have a clearer understanding of the semantics that we need to communicate across the web. At its most basic, an issue could be described in just a short string of text. For example, the application fails when clicking on button X in screen Y. Additionally, it is often desirable to include a more detailed description of the issue. Consider the following extremely simple definition. Issue title description optional. This definition is potentially sufficient for someone to take this issue and resolve it. Although the issue contains no information about who created it or when, it is possible to capture that information from available ambient information when the request to create the issue is made. Having this extremely minimalist representation of an issue provides a very low barrier of entry that can later be evolved. It is good for getting a working application for demo purposes, and it is also useful for low-power clients like phones. There is nothing to stop someone from later using a more powerful client to fill in additional data. Subdomains. Before charging ahead and implementing this minimal representation, let's get a better understanding of the larger set of data that can be associated with an issue. For organizational purposes, I have broken down the information into 4 subdomains: descriptive, categorization, current state, and historical. Descriptive. The descriptive subdomain includes the information we already discussed, such as title and description, but also environmental information, such as software version, host operating system, hardware specifications, steps to reproduce, and screen captures. Any information used to provide precision about the situation that produced the issue will fall into this subdomain. One important characteristic of this information is that it is primarily just human readable. It does not tend to affect the issue workflow or impact any kind of algorithms. Categorization. These pieces of information are used to help deal with sets of issues in meaningful groups. Attributes that belong to a certain predefined domain of values can be attached to an issue for the purpose of classifying issues for processing. Examples of this type of information include priority, severity, software module, application area, and issue type. Defect, feature, etc. This information is used for searching, filtering, and grouping and is often used to dictate application workflow. Generally, this information is specified early on in the issue lifecycle and does not change unless information was specified erroneously. Current state. An issue will generally have a set of attributes that define its current state. This includes information such as the current workflow state, the person actively assigned to the issue, hours remaining, and percent complete. This information will change numerous times over the life of an issue. It can also be used as classification attributes. The current state of an issue may also be annotated with textual comments. Historical information is usually a record of an issue's current state at a prior point in time. This information is generally not important for the processing of the issue, but may be useful for analytics of past issues, or investigating the history of an individual issue. Related resources. All of these information attributes that we mentioned will likely be represented in one of two ways, either by a simple serialization of the native data type, for example, strings, dates, Boolean, or via an identifier that represents another resource. For example, for identifying the people who are involved, we might have issue found by and issue resolved by. We could simply include a string value, but it would be much more valuable to have a resource identifier, as it is likely that the users of the issue tracking system would be exposed as resources. The natural choice for a resource identifier is a URL. By using a URL, we give the client software the opportunity to discover additional information about the person involved by dereferencing the URL. This separation of issue attributes and person attributes into two distinct resources is useful also because the information contained in those two resources has very different lifetimes. The volatility of the data is different and therefore will likely have a different caching strategy. It is likely that we will not want to display a URL to a human who is viewing the issue representation. We address this by way of a link. Usually, we do not embed URLs directly into representations, as there is often other metadata that is associated with the URL. A link is a URL with its associated metadata, and one standardized piece of metadata is a title attribute. The title attribute is intended to provide a human-readable version of the URL. This gives us the best of both worlds: an embedded, human-readable description and a URL that points to a distinct resource that contains additional information about the related person. Here is an example of a related resource. App blows up. Pressing 3 buttons at once causes crash. Title equals found by. Ref equals http://example.org/API/user/bot/. Attribute groups. Sometimes it is useful to group attributes together. This can help to make a representation easier to read. The groups can sometimes be used to simplify client code when a set of attributes can be processed as a whole. Perhaps a user agent does not want to deal with environmental attributes and therefore an entire group can be ignored. It is also possible to use attribute groups to introduce a conditional requirement for mandatory information. For example, if you include group X, then you must include attribute Y in the group. This allows us to support a very minimal representation but still ensure that key information is provided if a particular aspect of the issue is to be included. One specific example of this might be that when you include a history record that specifies the state of an issue at an earlier point in time, you must also provide the date and time attribute. There is, however, a danger to having groups and using those groups within a media type. Deciding that an attribute has been put in a wrong group and moving it to a new group may end up being a breaking change. so it is important to be cautious with the use of groups. Here is an example of an attribute group. App blows up. Windows Me. 284 megabytes. 1.2 gigabyte. Collections of attribute groups. Attribute groups can be used when you want to represent a multiplicity in parts of a